So thank you very much for coming to this talk series, which is jointly um, organized by the Hong Kong Academy of Gifted Education, the Education Bureau, and also the Young Academy of Sciences of Hong Kong. And also, so we're very excited to see you here. This talk originally was supposed to be in April because April was the Earth Day, all right? So every year there will be the Earth Day, really celebrating, well, I should say, really celebrating the beauty of the Earth, but at the same time, really promoting the awareness of protecting the environment of the COVID-19 pandemic. Everything is kind of like pushed up a bit. I believe a lot of you were not able to really go to school and you have to use Zoom educational stuff. So this talk or this sort of talk series has been moved to June. But we still wanted to sort of like relate it to the Earth Day. And we are definitely experiencing some of the greatest environmental, economic, and social changes in our time. And today, what we're going to do is to talk about the science and the technology behind. First of all, I'm going to talk about the science behind, like how do we indeed try to, when you think about environmental problems or understanding what the Earth is going through, it's undergoing. You can really imagine, how do we even try to understand the Earth? So in the very first part, I'm going to spend about half an hour sort of introducing some basic principles or what is the frontier of scientific approaches in order to understand what is going on in the Earth. How do we even know temperature is rising? How do we even know the Earth is actually changing rapidly? How do we even know that? So we are going to go through that. And in the second part by Professor Lu, she will talk about how we are going to use the frontier technology and engineering solutions to try to solve some of the greatest environmental problems facing us today. So today will be both about science and technology and how we are going to use both of them to move our planet forward to have a sustainable future. So that would be my introduction right now. So we can start the first talk. Okay, great. So I'm going to start the very first part. And first of all, I would just like to have a rough show of hand. How many of you are science teacher or students, or you study science subject? Okay, all of you. Okay, well, almost all of you. Okay. What about like geography? Have you anyone studying geography? Okay, good. All right. Okay, not really. Well, which is good, which is okay, which is totally fine. Indeed, today, one of the message that I would like to sort of like bring to you is that many people thought, all right, addressing environmental issues, you definitely need a lot of geography knowledge. But that is in a sense true. But at the same time, today, what I'm really going to focus on is the scientific principles behind. Indeed, we need to understand, say, mathematics, physics, chemistry, and biology, all of these disciplines in order to understand what is going on in the Earth and how we are going to solve them. So a lot of people may think, environmental science, is it just about biology or is it just about geography? And today I'm going to show you that, no, it's a lot about physics, mathematics, computation, statistics, and chemistry as well. All right, and indeed, I myself, I'm a physical scientist. I study mostly the chemistry and physics of the atmosphere and climate. All right, and also the ecosystems. And through my research, I'm able to address a lot of issues that is related to the environment and ecosystems as well. Yeah, so you're really going to see understanding environmental problems and sustainability problems is not only within the realm of, say, biology or geography. Everybody, all scientists and engineers can be involved in it, and their roles are extremely important. So this is one of the key messages that I would like to bring forward today. All right, so just a little bit to introduce myself. I'm Amos. I'm an associate professor in the Earth System Science program in the Faculty of Science at the Chinese University of Hong Kong. Yeah, and I'm an atmospheric scientist by training. So I study about climate change, weather, so what is going on in the atmosphere. And in particular, I look a lot at how atmosphere would interact with the biosphere, okay? So really understanding how plants and vegetation influence the atmosphere. And at the same time, As I mentioned in the introduction, we are definitely going through some of the greatest economic, social, and environmental changes in the Earth's history, really. We are undergoing rapid environmental change that indeed we haven't really seen before in the 4.6 billion years in Earth's lifetime. I mean, in terms of the rate of change. Of course, the Earth has been through many stages where temperature is really high or temperature is really low. There have been fluctuations of climate all throughout the Earth. But the rate of change, how fast things are changing, right now is indeed rather unprecedented in the Earth's history. All right, human beings are really changing the Earth's environment at a very, very accelerated and unprecedented rate. So, well, first of all, let's celebrate a little bit about the success of the human story. All right. So over the past 2 centuries, definitely our life expectancy have been increasing, which is great news. Poverty has been reducing. Poverty rate, the rate of people living under poverty, like below the poverty line, have been decreasing over time. Okay. And child mortality has been improving a lot. So in a sense, we're definitely living in a world that is much better than a few generations ago. Okay, we are having longer life. We are having overall, on average, better economic opportunities and better economic life, better income, higher life expectancy. We're living longer. Our children also survive better. And these are definitely things to celebrate. However, and human population is healthier in a sense than ever before because we have better nutrition, we have better access to clean water, and also we have a much better healthcare system, which can really help us sort of like reduce mortality or reduce the dire consequences of many diseases. So, but at the same time, as you see here, planetary health is a very interesting concept. Let's see. Now, okay. On an individual level, human population is healthier than before. So, but what about the environment? And would the changes in the environment associated with all of these big progress harm us at the end? Let's see. In order to achieve all of those development, okay, economic growth, better healthcare, and so on and so forth at an individual level, okay, or focus on human being. To achieve all of this, we have actually exploited the planet also at an unprecedented rate. You can really see that. Carbon dioxide concentration has been rising, and later I'm going to talk to you about like how do we even know that. The ocean has been acidifying. All right, we are really damaging the ocean ecosystems at a very, very fast rate. We are using energy at a rate that has never been seen before. We are causing the very precious tropical forest loss. The forests are really losing at a alarming rate. Okay, and we are using up water. Freshwater resources have been depleting. We are using so much fertilizer to drive our food production. Well, because we have been growing, right? The population has been growing. And in order to feed a growing population, we have been using so much fertilizer. And the fertilizer use indeed is one of the greatest source of pollutants in the environment, all right? Leading to air pollution, climate change. All of these issues have something to do with fertilizer use, all right? So we're definitely adding a lot of things into the atmosphere and the environment that are actually very bad for life in general and also bad for human health as well. And we're also changing climate. So this period of environmental changes introduced by our exploitation of the planet indeed defines a new geological era. We call it the Anthropocene. So we are changing the Earth, sort of the surface, the environment so rapidly that indeed, if a few thousand years later, when people look back at the geological record right now, we are totally changing the geological record as well. So we are an agent of change in a sense, and we can even call ourselves changing the face of the earth. And we really expect that the current trajectory we put even more pressure on the planet in the future, right? We can expect China is growing very fast, India is also growing very fast, and the rest of the developing countries, even sub-Saharan Africa, Latin America, okay, and South Asia, all of them are growing at a very rapid rate economically, and at the same time, they are trying to all of people in the developing countries. They also try to catch up with the living standard of the so to speak, the first world or developed country, and that would put even more pressure on the Earth's environment. Population is going to grow by probably to about 10 billion by year 2050. And in order to feed this growing population, and also more people want to eat more meat now, okay, than before. And later, we are also going to sort of talk a little bit about or discuss about, well, the demand for meat is indeed one of the greatest driver for environmental change, because to produce 1 pound of meat, 1 calorie of meat, it uses a lot more resources than producing 1 calorie of, say, grains or vegetables. So these are, because of, the rising population, the higher rising population, and also the higher demand for meat from the general population, we may have to double our food production in order to feed the whole world in the by about 30 years time. Okay, and the bad news is that we definitely do not have that capacity to double our food production, and of course our water demand as well. So the concept of planetary health is that even though on an individual level, on average, our life is better because of better nutrition, better healthcare, and so on and so forth, but we are also damaging the health of the planet at an unprecedented rate. And all of these things, all of these changes in the environment would ultimately hurt our health, okay? Because climate change driven by the rising CO2 level and other greenhouse gases will cause a lot of severe problems that would harm populations. All right, today I may not focus too much on the individuals, disasters arising from climate change. We can discuss that later. But yeah, climate change definitely is causing a lot of, up to about a few tens of thousands of, a few 100,000 of deaths per year, because of the disasters coming through it, because of the warming, and because of the spread of tropical diseases, and so on and so forth. Many, many causes behind climate change would hurt people to this level. We are really changing biodiversity. And the climate change and other environmental changes are also sort of hurting our food production. Yeah, so even though for the past century, we are able to produce more food, but our ability to produce more food is really constrained by the environmental changes. Climate change and pollution really hurt agricultural production, as I'm going to talk a little bit more about, because that is what I do for my research. And other impacts. All of these things would ultimately harm the health of human beings. So the idea here, it really is, in order to safeguard human health, we need to maintain the health of the planet on which we depend on. So this framework is the very important framework to look at environmental changes today. Because a lot of people still talk about the environment as if it is separate or not really related to them, okay? So a lot of people still think about climate change as if a problem for the polar bears. But the reality is all of these environmental changes, climate change or pollution, they're hurting our very own health, because they're reducing food production, they're causing more pollutants that damage your individual health, and also causing a lot of more disasters, which put people at health risk. All of these things ultimately would be harming us. So this new framework of really seeing our own health and environmental health together in the framework of planetary health is really the dominant or the sort of emergent, very important approach to address environmental issues today. So this is just to give you a framework of how we think about environmental problems right now. It is really a holistic view. integrating our own well-being with the well-being of the planet. And I'm not going to talk about these today because, like, we may be talking about then how are we going to deal with all of these issues. Definitely, there are many, many things we can do about it on an individual level, okay? And I'm sure you must have discussed, heard about these approaches like, reduce food waste or having better energy efficiency, so on and so forth. This is not what we are going to focus on today, because we want to sort of share with you how scientists and engineers, and by doing science and technology, how we are going to address these issues. So I'm going to introduce, so what do scientists actually do? We understand that the environment, the whole Earth, is a very, very complex system. All of the Earth's components, like the atmosphere, the biosphere, the ocean, and human societies, they are all interacting with each other through many different pathways, okay? And how do we even study such kind of complex system, okay? How do we even understand what is going on in the environment? We can't really do experiments on the environment. How do we even know what's going on? So we really do want to have a physical understanding and also projections, meaning a predictive ability of global environmental change in an Earth system context, which means we understand that all of these things, the atmosphere, biosphere, ocean, the land surface, and human societies, they are so intertwined with each other, and we have to understand their interactions as much as understanding individual processes governing their own component. And we want to understand the implications of environmental change and try to think of solutions for these very complex issues, all right? And Professor Lu is going to talk more about the solutions part. But first of all, how do we even derive that physical understanding? And in relation to food, water, energy, human health, all of these things, to understand all of these things, all right, how environmental changes will affect food, water, energy, and our health, we are really considering a lot of complex processes happening in the Earth, all right? So now I'm going to focus on what do scientists do, okay? How do we understand the Earth? So this would be the sort of like a generic outline that sort of summary of the major approaches and the very sort of frontier and interdisciplinary approaches that environmental and earth scientists are using to understand what's going on in the Earth, okay? How do we even know there are problems? So you can think of it like we environmental scientists are kind of like the Earth's doctor, okay? We are using different things, different methods to diagnose the health problems of the planet, all right? And I'm going to draw connections with, like a medical doctor, with, so to speak, planetary doctor that we are trying to be right now. So, but this looks very complicated, but I'm going to go through it sort of like a bit by bit. Well, since many of you are science students, doing laboratory or field experiments are definitely something that I'm sure science students would know that, okay, scientists work by doing experiments, okay? So doing controlled experiment, you go to a lab or you go into the field, you try to set up a control, and then you change certain parameters or design your own experiment, leading to some result that for you to understand what is going on, okay, so on and so forth. I'm sure doing laboratory and field experiments are definitely very important, like physicists, chemists, biologists, social scientists, all do this kind of experiments. And these experiments are very valuable for us because, for instance, okay, so we can go to a lab and try to mix different pollutants together and see their reaction rate and see their products, for instance, okay? Definitely some group of scientists would do that so that we can understand, the chemical reactions happening in the environment. We can understand, CO2 actually have a greenhouse effect. It would absorb, infrared radiation, we radiate it, so on and so forth, okay? So doing experiments are definitely very important. Okay, and this is I believe most of the science at the secondary school level would think of science as basically doing experiments, okay? But when you think about it, there are already problems. But how are you going to be sure that what happens in the experiment, in the lab, okay, in the lab in your school, for instance, is actually really happening in the environment, right? In the lab, you have to set a particular temperature and set a particular, so to speak, conditions for your experiment to run. But in the real world, temperature is changing everywhere, or the environmental conditions, the amount of water, humidity, things like that, they're changing all the time, right? How do we even, replicate what's going on in the environment in our lab? So that definitely is a very, very large limitations, right? Because in the laboratory, we cannot simply replicate what's going on really in the environment. So indeed, environmental and earth scientists have relied a lot on other non-experimental methods to understand the earth, okay? And today I'm going to focus a little bit more on that. Not to say that these are not important, but these have a lot of limitations because the lab is not the real world. But these are still very important, the experiments, to provide us with important, say, the rate of reaction or important parameters that are needed to calculate, the emergence of new pollutants or so on and so forth. So this is still very important, but in order to understand what's going on in the whole Earth and in the environment, we rely on two other very important things. One, observations. Observations meaning really going out there to measure the variables that you want: pollutant concentration, greenhouse gas emission, temperature, humidity, life, like how many birds you have there, how many insects you have there, a lot of different kind of things. You really go out there to do the measurements. And in particular, you don't only go out there to do the measurement on the ground. We can even send satellites, okay, to space, and have the satellites really monitoring what is going on in the Earth. So all of these, we put it as we can basically, they are all observations, and observations are indeed very, very, very important for environmental science. Okay, so it's not exactly experiments where just go out there checking what is going on. But this is indeed very important because we need the observations to really know what's going on in the Earth. So the state-of-the-art sciences really involved different ways of checking or measuring what's out there. One of the big advances over the past 2 decades, okay, in terms of really advancing our understanding of the Earth and environment, is the use of satellite. So satellite is very powerful. You're really sending out like a satellite up there, and then these satellite can orbit around the Earth in different ways. Some of it only stay at one single location and follow the Earth's rotation, so that they can continuously monitor one place with very high temporal coverage. Some of them would always orbit around the Earth, okay, and then they may not be able to check every single place every single minute because it is moving around. But when they move enough amount of round of time surrounding the Earth, okay, they can have at least a good spatial coverage. Okay, that may not have very good temporal coverage. Maybe you can only get some average over the month, but that's still very good. Okay, so yeah, so you can have some satellite really orbiting the Earth like that, and to get a very good spatial coverage. So, and satellites, what are really satellites measuring? Okay, if you have studied physics, probably you know that satellites basically just care about the wave or electromagnetic wave. Well, or I should say radiation. Okay, so it is not exactly checking, or measuring the exact thing they are trying to measure. It's not exactly measuring the concentration of things or of chemicals or the surface properties of the Earth. What they are really measuring is just radiation, light. What kind of radiation? Well, the sun always have solar radiation shining onto the Earth, and different objects can have different reflective properties. You know that, right? Like the things that are white would reflect more sunlight. Things that are black would absorb more sunlight and thus reflect less. And indeed, most of different things would have their own optical property or reflective property. And thus, by really measuring the kind of solar radiation that get reflected by different things, we can understand what's on the Earth's surface and how they're changing over time. For instance, this is a satellite image from using visible light and basically checking the reflection from visible light. You can really see that, identify places where you would have vegetation and places where you have urban area, because vegetation and urban area would interact differently with light. Okay, and vegetation is usually darker, and bare land is usually lighter or have different kinds of optical property, and you can really see that from the satellite. And if you measure it, if the satellite monitor it over time, you can really see the long-term changes in the land surface, land cover. Well, another things that satellite usually measure is also radiation, but maybe not visible light, but the infrared radiation. Even when the sun is gone, okay, even when the sun is gone, the Earth's surface is still warm enough to emit infrared radiation. Yeah, so there's still radiation going on at night, all right? The Earth's surface, anything that has a temperature would emit radiation. And the Earth's temperature would still be warm enough to emit infrared radiation. So by checking, by sort of measuring the infrared radiation or thermal radiation from the surface, you can also get to understand that, identify different things that is going on. And also even the concentration of different chemicals in the atmosphere as well. So satellite images have been a very, very crucial sort of channel method for us to understand what has been going on in the Earth. It's the satellite image, okay, that really tell us how much ice has melted over the past 30 years because of climate change. All right, you can really see here that, well, about 30 years ago or so, the sea ice extent in summer is much, much larger than it is last year, right? So by having a series, multiple, like a few decades of satellite image, we can really see the extent of the melting of sea ice. And if without satellite image or satellite observations, these kind of conclusions cannot be really drawn. And more recently, we can even use satellite image to monitor the concentration of carbon dioxide. Okay, carbon dioxide interact with radiation, mostly interact with infrared radiation. So satellite images can help us identify places where there is a lot of CO2 emission, like obviously China, but in this particular season, there is also a lot of wildfires in the tropical regions. So you can also see a lot of CO2 there. Okay. And last year, we all understand that, we all know that, there have been a lot of forest fires around the world, in Australia, in the Amazon. And satellite can have also helped us exactly identify the extent and frequency of wildfires, because obviously fires give off radiation that is very different from the surrounding vegetation. So the satellite can definitely help us monitor what is going on and understand the spatial extent of such catastrophes. And like I said, well, satellite help us understand the kind of land use changes that we have been through. Indeed, we are definitely, this is 2006. And this is 1990. Okay, sorry. So we know that even in this Pearl River Delta region, we have been undergoing very rapid urbanization. Okay, sorry about that. Like the year should be swapped. All right, now we have a lot more urban areas than the land. And I'm going to talk a little bit about an example about how we use such to understand the kind of environmental changes we go through on Earth. I mean, in our city. And well, obviously, Satellite images can help us monitor air pollutants as well, and even tell us where they are most intense and where they're where they're flowing. Okay, so this is yeah, very, very useful for our science. Well, let me spend maybe a little bit more time. I'm sorry if I overrun a little bit. So observations are one of the three key elements understanding the environment. Observations are very important. Okay, they tell us what's going on, what is there. Okay, and what kind of changes there is. But then you may be wondering, yeah, I can observe things, but how do I know why? This is another thing that scientists really need to know, right? Yeah, you observe rising CO2 concentration. You observe rising temperature, so on and so forth. You observe all of these things, okay? But as scientists, we need to know why. What is causing the changes? And at the same time, we also need to know, okay, so now we know why. How are we going to do about it? What are we going to do about it? So observations alone are definitely not enough. Experiments alone are also not enough. As I've mentioned, experiments can tell you in part what the mechanisms behind. You know, sometimes when you do experiment and then you do control experiment, maybe changing one parameters and then see what's going on, you can at least know in part the mechanisms that is going on. Okay, but again, experiments are not the real world, so the lab is not the real world. So environmental and earth scientists rely on extremely powerful tools that are only able to be used in the past few decades because of the advance of supercomputers. So environmental and earth scientists rely a lot right now on numerical models or computer simulations, okay? Computer models. And we were only able to do so because of the advance of supercomputers over the past few decades. Right, even past 2 decades, actually, most of it. So what is it? How do we even use computer models, and what is really the use of it? The use of models have two major uses. Okay, one use is you can actually use the model to understand why, to understand the mechanisms behind. Because the model, you can use the model, you can basically put all of the scientific understanding in the form of mathematical equations into the model, and then you can use the model to run experiments. So we cannot run the experiment on the whole Earth, right? Because that's just not ethically impossible. But you can use the computer to simulate the real world using mathematical equations, okay? Then you can use the model to perform experiments. All right, because of course you can use your computer to do whatever you want, right? And then you can use the computer to do experiments, and just like what you do in a lab, but instead of really mixing things in a test tube, you're doing it in a computer, and we can then discover and know, so what is going on in the environment. And another very important uses of computer model, and only computer models can do so, is to predict, to really predict what will happen in the future, given certain scenarios. So we often hear about scientists telling you, oh, the Earth's temperature is going to rise by like 2 degrees Celsius in the future, or the Amazon forest is going to die, or die back in about 20 years' time, so on and so forth. All of these of actually results from computer simulations, okay? So just a little bit more about mathematical, these computer models. What were we really talking about? Computer models are basically, mathematical model. We characterize everything we know about the environment, mostly from experiments, okay? We then know the equations and so on and so forth. We then try to put all of those equations, mathematical equations, representing the physics, the chemistry, even the biology of the environment, and we put all of these mathematical equations into the computer. Sorry, we code them, and we code them into the computer, and then ask the computer to solve those equations for us. And then, yeah, that is basically the principle of mathematical modeling. So for instance, what we usually do is to divide the whole Earth into many grid cells. And in each grid cell, we try to solve the equations for the chemistry, biology, and the physics, okay? Like fluid physics, chemical reaction, all of these fluxes, some biology, photosynthesis, things like that as well. And then we can predict what's going on. So, well, basically here, I'm just trying to show you that these models right now are really advanced. They can have very high resolution, meaning they can really represent even a cities, okay? And the different features of a region, different vegetation form, different hydrology, and they can really resolve things at a very high resolution, okay? And some of them and we put the observations into the computer models and then run the simulations to see, to do prediction and also to understand what is changing or what is going on in the environment. So here I'm just going to show you a couple of examples before I have to end. This one is done by my colleague, okay, Francis Tam. So this is a very good case study of like integrating observations and computer model to help us understand what's going on in the environment and think about how to solve it. So what their team has done is to use satellite images, obviously, to understand the changes in the land cover over the past few decades. And then based on that, he can project future changes of land use. So we predict that urban land use is going to intensify in the next 10 years or so. Okay, so this is like a combination of satellite images and predictions based on satellite images. But what he is interested in knowing is, well, how will urbanization affect the temperature of Hong Kong or of Pearl River Delta region? Okay, in the context of global climate change. So what he is trying to understand is like, well, urbanization is happening, and at the same time, global warming caused by rising CO2 is also happening. So the two things are actually separate, right? Urbanization is one process, global climate change is one process. How will these two things contribute to the rising temperature of Hong Kong and Pearl River Delta region? And then he see that basically by using the computer models, he is able to diagnose that urbanization will exacerbate high rainfall in Pearl River Delta region, okay? And indeed, urbanization has a comparable effect with global warming. So it's kind of like if temperature rises by, say, 3 degrees in Hong Kong in the future, half of it, maybe 1.5 degree, is because of global climate change, something that Hong Kong alone cannot really solve, right? Because rising CO2 requires multi-international effort in order to reduce, okay, in order to mitigate. But at least half of the temperature rise that Hong Kong and Pearl River Delta will experience is actually coming from urbanization, not exactly from global climate change. And this is something that local people or the government can deal with. They can think about better urban planning. They can develop the urban setting better, and also maybe advance more or sort of build more urban greening projects in order to reduce the impacts of urbanization. This is something that definitely local governments can help. And by identifying the factors that are really contributing to the warming environments of Hong Kong, we can then start thinking about solution. And instead of feeling helpless, because a lot of people would be like, well, global warming is so hard to solve, like it requires international effort. How can even a single city deal with it? But here we are really showing that, well, we can, because part of the warming is actually from urbanization instead of from global warming per se. And at least that part can be dealt with. I'm going to give one last example, and then I have to stop because of the time being. Another environmental issues that I myself work on is ozone problem. Ozone is like a 草原, okay? So ozone is a good thing when it is very high up in the sky. They protect us from UV radiation. But ozone, if they exist around us, is very bad for our health. So it is one of the two major air pollutants that harm our health. Another one is PM 2.5, like right? Like those particles flowing around. But ozone as a gas is also very, very damaging to our health. So by also integrating global observations with computer models, I am able to predict that there would be great threat from both climate change and ozone air pollution to food security. So what we did is that we used the model, a computer model, to project future climate and future ozone air pollutant level. And indeed, ozone itself really, really harms plants and crops, okay? Because it's a very strong oxidizing agent. And in this research, we thus are able to really see that warming and ozone pollution causes global crop loss of crop production, and that loss is really, really huge. But even if we cannot mitigate climate change, if we control ozone by performing ozone regulation, because this ozone is an air pollutant that can more easily controlled by local authorities and governments. And indeed, ozone regulation can cut that loss to just 9% and undernourishment greatly by 50%. So what we really show here is pollution control can have substantial co-benefits for both human health and food security. All right. So when you try to regulate air quality, okay, usually it is for the sake of human health. But what we have shown by the modeling and integration with data is that controlling air pollution can also help reduce food insecurity, because if you reduce air pollutants, the crops are going to grow better. And then the problem of food insecurity can also partly be solved. Okay? So I'm going to skip most of these things because of the time being. But I would just like to leave it at this. Okay, we can discuss more about it in the in this discussion session. We have a long discussion session today anyway. But to summarize or to conclude, to understand what is going on in the environment, we require three major tools, and not only one of them doesn't really work. We need to have few experiments, okay? We need to do experiment to kind of know the basic parameters that we need to put into the model, or to just know understand the mechanisms behind. But definitely a lot of observations, and especially from remote sensing or satellite, okay? Where these observations can help us monitor the changes that is going on in the environment. But another tools that are very important, especially for people who like computers and coding or programming, computer models are very, very important tool to understand the environment. Partly because we just cannot perform experiment on the real environment. So we rely on computer models to do those experiments for us, okay, simulate the real world. And at the same time, using those models, and only the computer models can help us, one of the numerical models have been the major tool where we can derive predictions for the future. So these models are kind of like the crystal ball, okay? These models tell us what will happen in the future. But more in the recent years, more and more predictions have been relying on statistical methods and machine learning, in particular machine learning as well. So machine learning is another major new field of environmental research. So basically the idea is that in order to build computer models, you really need to understand the mechanism behind first so that you can code those equations into the computer. But again, we do not understand everything. So machine learning is basically kind of like, let's not care about what the actual mechanism. Let just the data tell us the patterns behind, and basically use the patterns based on the historical patterns to do future projections. All right, today I don't have too much time going on with that, but I guess the main idea is that machine learning and high performance computation is one of the major key sort of methods for us to help us understand how we can have a more sustainable future in the sustainable planet in the future. And with that, I would like to close, and then we'll have a break right now, and afterwards we'll move on to Professor Lu.
Good morning, everyone. Let me just stand before I sit down, because I usually stand when I talk. So my name is Yi-Chun Lu. I'm from Chinese University of Hong Kong. I'm from the engineering faculty. My background is in material science and engineering. I got my bachelor degree in Taiwan National Tsinghua University and my PhD at MIT, also in material science. I've moved to Hong Kong 2013, and since then I've been working on energy storage. So today we'll be sharing some of our recent work, but really put into a context of why we want to learn science and engineering and science and technology. How is this going to play a role in your generation? Okay. So I want to start by asking some of the questions, really to think about why things happen the way it is today. So if you see, if I can, I don't know how to, where's my screen? Can you see my, oh, here, there you go. Oh, it's very tough. Okay. So if you look at the Industrial Revolution, why things happen the way they did is the economic activity drive. So we need to fulfill our, we need to eat enough and then survive. And so things start, we have the first generation of the Industrial Revolution. Depending on the steam and coal, we burn steam and coal to get energy, right? And then we will have economic activity. After that, we start to electrification. You know, we think we want something faster, we want something higher power, again, to fulfill the economic growth. And that's why scientists, engineers invent ways to, let's not burn the coal, that's electrify things. So that's much, much more efficient. But you can see this first and second generation has created this huge problem of dilemma of economic and environmental impact. So Professor Amos right now in Earth, but really this is why we did this to Earth, because of economic need, right? So in this two generations, you see, so in order to have economic growth, we need to sacrifice Earth. So it seems that that's the way it is. But is it true that we have to stick to this dilemma? Can we break through this dilemma? Can we have economic growth at the same time protect our Earth and do things that's good for our Earth? So I think in the third generation, it's happening right now. Today, internet, of course, everyone can access internet. And the second part of the third generation is the renewable energy, that the new energy era is coming, that we can actually grow our economy at the same time, make sure that we protect our Earth. And I think that's very meaningful. The first time that we can see this being helping each other, not necessarily sabotaging each other. Okay, so that's really my hope. and also a lot of scientists and engineers try to make this happen. And I think you, as students living in this field or learning this field, really can contribute. How can we make this true, that we can grow economic, but also help our Earth, right? So that's something we need to start working on. Okay. And another thing I want to mention here, kind of echo Amos, is that a lot of developing country or the developed country, they're already past first and second generation. They are rich, they're developed now. But if the developing country use the exact same way how they get there, we will definitely be hopeless, because they will burn as even more coal, they will burn even more Earth's resources to get there. And that's not gonna be sustainable for sure. So creating solutions for them to grow economy at the same time with a sustainable way, that's the only path that we can go to that level. Otherwise, they will just continue to repeat the history. And we can't blame them because they want to grow the economy. All right, the developed country already did. So what can we offer that to help them? So this is kind of like a breakdown into energy demand, right? So okay, we want to help them, and we want to think about, population is growing every year. So in order to meet this energy demand, what kind of new energy solution we need to create in order to meet that demand? So if you look at this, this is, just kind of keeping, this is the energy demand right now. If we just keep everything for fossil fuel, for simplicity, we still have a long way to catch up. We need to use other solutions, right? We cannot today cut all the oil yet. We want to, but we cannot cut it all yet today. So we need to develop other methods to kind of cope with it. So we call it like a cocktail solution, because you cannot say, oh, the renewable energy is so tiny fraction, and so it's not important. That's wrong. You have to develop it while we can, right? So it's gonna be a cocktail solution, meaning that we need to encourage a different type of clean energy solution. And no matter how tiny it may seem right now, it doesn't matter, because it's gonna play an important role someday and to save all of us. So, for example, for solar energy, we all know solar energy is enormous. Just every day, every second, the sun shine on Earth will sustain us for a long time. But what's the way to capture it? Has scientists figured out the best way? So that's something that is kind of like it's really a mentality, right? So also, as I'm an experimentalist, and it's very exciting to see your own invention and to just contribute to this grand scheme of framework, the dream that you can see a little one step by one step that this can be eventually realized. So here are some examples of how the current energy technology is trying to combine sort of a holistic solution together with an existing one, because it's not trying to take away or remove, but just develop while we could right now. Solar energy, and then of course electric vehicle. It's very popular in Hong Kong, and also wind energy, also biomass on the left. You can actually use some of the waste bio, and then we can also apply those renewable energy into our daily smart city planning. So we call it smart grid. So how can we improve the traditional inefficient grid to a smart grid that can large scale using the the renewable energy. Because renewable energy right now, actually, if you don't do it well, it would be a burden to the grid because it's so unpredictable and so fluctuating. So some people told me actually in some part of Germany, because they have already very wide penetration of the solar panel, and that because then you will generate too much unreliable or unpredicted power into the grid and create problems. And so, but how can we make them all together into a more positive and helping way is still undergoing. And also, so far, solar energy has not been connected to electric vehicle. But today, I saw a press release from Tesla. I think they're going to build a solar panel on the top of the car for Model X next version. This is really cool. Sort of see, it's not a dream anymore. It's really ongoing right now. So in addition to energy technology, it's also related to how we apply those energy technology to our daily life in our buildings. So, Hong Kong's building energy consumption is more than 70% of the entire Hong Kong energy consumption. So if you save 1% or 2% of the building energy consumption, that's a lot. So how can we use solar rooftop? How can we improve the air ventilation, reducing the need for the AC air conditioned? And so actually I've brought students to a very nice exhibition, like a real exhibition area called Zero Carbon Building in Hong Kong. So in that particular building, they achieved zero carbon emission, meaning that they offset all the carbon emission for when they build the building, so they can generate electricity by paying back the carbon emission they built in the beginning. And then they have self-sustaining power generation system by solar, by wind, also biomass. I went to this building. It's very modern look, interior and high technology using this indoor air quality control and so on. So a lot of green building technology can be implemented. Right? And so now currently it's not a tall building yet, but then scientists currently are trying to apply some of the existing knowledge and to the whole building that's very common in Hong Kong. So that's sort of another aspect in this. So we all know solar energy is one of the big factor for all this sustainable energy framework. In fact, technologically, it's very mature already. It can be very inexpensively manufactured. But the problem right now is the efficiency is still not very high, which means that you cannot get as much energy with a small area. So Hong Kong does not have much land, so it's hard to put something like this solar farm in Hong Kong, and there's not much area for rooftop because we have only tall buildings. So scientists try to improve the efficiency. So if we can improve the efficiency from, let's say, 12% to 20% to 30%, then we can reduce the area we need and to generate enough power. And so that's something is ongoing in the scientific community. So how do we improve efficiency for photovoltaic? I believe that in order to do any improvement, you need to understand how it works. Right? So I'm sure some of you know how photovoltaic work, but it really depends. It uses a semiconductor. For example, silicon. You can have a p-type doped semiconductor and the n-type doped semiconductor using 3-5 elements. And then once you combine them to create a p-n junction, what happens? So the p-n junction will create a depletion zone where the positive charge want to migrate from P to N, and then negative charge want to migrate from N to P. And after a certain point, it will stop because then you create a built-in potential that will contradict to the migration. Right? So that balance will be complete. And then that's a perfect way for us to utilize this voltage. Right? We know that if you connect an external circuit, you can actually utilize this built-in voltage. So then in a very small scale, this is what a solar cell looked like. And so when you shine the photon into the solar cell, you will create the electron-hole pair. And the electron-hole pair will sense this built-in potential and move according a lot of electron hole pairs, and it creates a lot of currents. Okay, so by looking at this, how do we improve efficiency? Well, there's many things you can think about. Well, first of all, we need to have high quality, defects-free semiconductor, because each time if you have lots of defects, the electron hole pair will be captured, will be eliminated because of defects. So we need to have high defects. What else? We also want to have a high conversion. So band gap is important, right? If band gap too high, band gap too low, we will not be better utilize the photon range, right? So there's a lot of materials that you can tune and then to change this efficiency. Okay. So solar is great, wind is great, but they are not enough because they are not stable. So in order to provide sustainable and reliable power, we need something called energy storage. We need something that can store the power when we have and then supply to the user when they need. So you can look at, typically we look at energy storage for a stationary, for the grid, or automobile for the electric vehicle. So this is just to show you how fluctuating and how unreliable for solar and the wind. This is their power generation curve. This is basically, of course, on the noon of the day, you have the highest solar power, but then it will decay once you go into the evening. And then in the cloudy day, you really don't have a good say of what's going to happen. The wind is even more unreliable, right? So, and that is the main reason we still cannot use massive of solar energy because it's not reliable. In addition to that, energy storage is also important to help us to remove the peak that in the power generation. So here you can see on the blue curve, this is a power generation curve, let's say CLP need to generate in order to fulfill Hong Kong demand. So you can see the blue one, meaning that in the beginning, people are still sleeping, there's not much demand. During the work hour, it's increasing, and when everybody go home, turn on the TV, turn on the air conditions, there's a peak demand, right? And so in order to fulfill that peak power, CLP needs to be able to generate everything at this power peak, meaning that otherwise they will always have a power outage whenever everyone starts using it, right? So they need to be prepared. But in order to get that point, the generation capacity needs to be enormously much higher than the overall need. And so that costs money. And who pays for the bill? You, right? Us. We pay the bill. And so it's inefficient. We lost most of the energy and it's expensive. So what if we can have a reliable energy storage device that we can charge to the battery when everyone is sleeping, and we can use very low cost electricity to charge it. And then we store them, and when we're going back to the peak, instead of the power plant generating here, we make the power plant generate the flat curve, and we can make this what we save in the morning back to the evening. And so all of a sudden, just by putting the battery in the power plant, you can make this generation profile much smoother. And even without using renewable energy, you can save a lot of energy and money. So energy storage is important not only because the intermittency of renewable energy, but also important for the grid. Okay. So there are lots of market opportunity, right? So that's why in the beginning I said we don't necessarily have to separate environmental consideration with economic, right? They could be hand in hand. So there are a lot of market potential for energy storage technology in solar photovoltaic and then some battery, and then we can really provide sustainable energy for that remote area without extending our grid. Right? Also, we can have electric vehicle using electricity from solar, and that itself is also very clean, right? So there's a tremendous amount of opportunity in making the earth better and making economic better. So, from generation to the users, from the grid to the smart city to the personal electric vehicle, you need energy storage from left to right, right? And every one of you are using one of the energy storage device right now, your cell phone, your laptop. And so this is sort of the vision of Tesla. They're using this, they want to create this kind of home where you can have generate electricity from your solar photovoltaic and store in a battery. They have the Tesla Power, and then you have generate basically sustainable for your personal use. So all of these are great, but obviously we're not there yet. Why? Because it's expensive and it's also not very safe. Okay. But before we can improve it, what do we need to do? We need to know how it works. So how does a battery work? So in a very, very simple manner, so in the battery, you have three parts. One is a positive electrodes and a negative electrodes, okay? In the middle, you have a ionic channel that will block electrical conduction within the cell, but provide ionic conduction, okay? And so we also need an ion carrier, charge carrier. So you can have lithium ion, or you can have other type of ion, sodium ion, potassium ion. And this ion has different electro potential or energy level in different electrodes. And so during discharge, the ions sitting at higher energy level will naturally, spontaneously want to migrate to the lower energy level to release its energy. During this time, the electron will go external circuits. And so that will light up your light bulb, your cell phone, your laptop. And so this process, we let the high energy ion migrate from high energy level to low energy level. So then how do we recharge it? So simply we convert electrical energy to force the low energy ion move back to the high energy level. This will not happen spontaneously if you just let it sit there, right? You need to improve electricity. And so then by doing that, you convert electric energy to chemical energy. So now the high energy ion now going back to the high energy state, and next time you can use it again. So that's how we convert electricity to energy, electrical energy into the battery. So I say it's dangerous because, even in daily and in your cell phone, your laptop, we are still using the electrolyte that will actually possibly cell burn, ignite at a certain temperature. And so this is a recent news. Actually, there are many, many news before May, but this is just one of the recent ones that you can see This is an electric vehicle. And then during the charging, you can see the wire. The temperature of the cell starts to rise and release some toxic gas. Okay, and that's during this process, you increase the temperature of the battery so high, such that to a point, the electrolyte in the battery will get ignited as it reaches the flash point. So now you start to see explosion from your battery. So not only they will burn their own car, they will start to burn other cars. And so this, at the end, sort of create this kind of thing, right? I mean, can you imagine this happen in your garage or in your neighbor's garage? No, right? You don't want it. But unfortunately, we know this will happen again because the battery itself is not safe. So that is just, cell phone battery can also burn, right? This is also from not long ago from the Galaxy Samsung 7. Laptop can also burn. Tesla can also burn. I mean, Tesla is very high tech, but because the fundamental risk is still there, we cannot prevent it 100%. And so this scale are big, but it can also be bigger. So if you put battery into grid, because we mentioned we want the grid to store energy. This is one of the incidents happened in Korea that they use a gigafactory for the battery to store solar and then the wind power, and that creates some incident there. And so, of course, they know there's a risk, and then they did a lot of things to prevent it, but things happen. And so one of the examples I want to show you today is by understanding why it happens, and then you generate idea to solve it. So first, let's see why it happens, right? So first of all, in your laptop, in your cell phone, if you have some shortage of your battery, once the shortage happens, remember we have a positive and negative electrode. They are at a different energy level. What happens if you short them using electric conduction? The energy will release in a very short time and generate heat. And so if we have short, the temperature will start to rise. But rise is okay. I mean, it's just getting hot. But after a certain point, the electrolyte, the liquid inside, because it's flammable, when it reaches the flash point, it will catch fire. So there's no way around it. So if you look at this, how can we prevent it? Well, you can completely solve it by using water-based electrolyte. So water-based electrolyte meaning that you remove the flammable electrolyte and only use water. But you say, wow, this is such a wonderful solution. Why don't we use it? Why don't we still use the flammable electrolyte? Well, because we need energy density too. We want something, you want your cell phone to last for at least a day before you need to charge it. You don't want it to last for 20 minutes and then you need to charge it. So you need high energy. That's why we still use the cell phone, we use battery right now. But water is good, but water cannot give you high energy because it will be limited by the voltage of your battery because the electrolyte will decompose when it's greater than 1.23 volt, when water will break down. Okay, so unfortunately, it's not a good news. So the scientists start to think, well, let's not give up just yet. Let's use water, but let's think about how to improve water. And so there's a lot of ongoing research, especially in the United States. A lot of scientists think maybe we can try to increase the voltage by adding a lot of salt. And they found that it's actually very effective. They can expand to 3 volts, from 1.23 to 3 volts, even 4 volts, without using flammable electrolyte. So that's a great idea, and that really sort of excites the field to developing the safer battery. But there are also disadvantages. The salts are typically very toxic and very expensive. And so when they use high concentration of salt, they're usually talking about 21 to 50 mole per kilogram, or in a weight percentage is about 85 to 95%. That means you remove most of the electrolyte, but you put a lot of salt. So it's expensive and toxic. So recently, we tried low-cost polymer, and that's called PEG, polyethylene glycol. Why do we think of this? Because this is a water miscible. It's not only soluble, it's miscible. It can mix with water at any ratio. And we want to use this to replace water or mix with water instead of putting a lot of salt. So that is the basic idea. And so this graph shows why PEG can help. This is our thinking. So if you have a lot of water, this free water will easily decompose when you have higher voltage. So with PEG, we can replace the water, but also lock the water down to a more stable, so they can generate hydrogen bonding. Freshman chemistry, nothing fancy, but putting a PEG with hydrogen bonding network that you can really stabilize water. So how much we can expand this? So you can see this is cyclic voltammetry. This means that the current as a function of potential, as you go lower potential, that's where hydrogen evolution starts. So regular water, you can go around this window, and these are the used other. But in our PEG electrolyte, using low-cost, environmental friendly PEG, you can get the highest window ever reported. And this means that if you use this electrolyte, you can be you don't have to be afraid of the explosion anymore. And then while at the same time, you can get high voltage. So you don't need to sacrifice anything, okay? So this is a more characterization to show that there is no hydrogen evolution in our data. So this is, red line is our data you have, and this is in other electrolyte that we compare. You can see in all cases, other electrolyte, even use high concentrated salt, you still have some hydrogen evolution. But with PEG, it's quite stable. And so we can expand this window, and so a lot of electromaterial can be utilized in the aqueous environment. So put into a simple way, now you have obtained a non-flammable electrolyte, but instead of using concentrated salt, you can use low cost. So what's a low cost? So compared to the current commercial electrolyte, about $7 to $20 per kilogram. And so also it's also very environmental friendly, that you can actually find this ingredient in your screen cream that you use every day, even some of your food additive. Right? So we are able to do more than 3.2 volt and can even reach 4 volts with some sort of coating. So this can really put us in a way that we can dream a safe battery that provides high energy. And this is really a pathway for us to be able to utilize more battery in a more relief way, right? So I don't have to worry if I build a gigawatt-hour factory. I don't have to worry about the fire issue. So this is the video show. This is the commercial electrolyte. If you put a fire on the electrolyte, it will continue to burn. But instead of burning our electrolyte, you can actually extinguish the fire using the electrolyte. So this will help you to remove fire. And so that is how we can sort of spot a problem, why people are afraid of moving forward with a lot of battery, because they're afraid of safety. So how can we use that? How can we solve that using environmental friendly material to help them to use more battery in the car, in the grid, and so on, right? Another example I want to show you is in the EV, we have many ways to recharge. For example, you can do fast charging, you can do battery swapping. Lots of people are working on hydrogen fuel cell, but they all have their own issue. For example, fast charging will actually decay your battery lifetime. Battery swapping is very costly, as you need 2 batteries for 1 car, and 1 battery already costs 1/3 of the car, so that's not very economically viable. Hydrogen fuel cell is great, but to transport or the infrastructure for hydrogen storage and transportation is pretty massive. So battery is still on the game, but how can we use different type of battery to help this fast energy supply for EV? Because I actually have a conversation with a taxi driver. One year he got a gift from BYD. So BYD give them a free electric vehicle to test drive. And actually after a year, he gave up, even though it's free. Because every day he needs to spend 5 hours to charge the battery. And for them, time is money, right? So the long time charging is not possible for them. So in our lab, we are working on an alternative solution called flow battery. So flow battery, it's interesting that we actually store the active material outside the battery. We put them into liquid form and circulate them inside and coming outside of the battery. So whenever you need to use the battery, you can circulate in, and then in the middle you can stack a lot of a pair, right? If you need 100 volts, then you can stack 50 cells, right? And so that can give you voltage. And so in this design, you can decouple the design of the energy need or the power need, right? And so that is very good because even though you have a car crash, you can immediately shut down the electrolyte into the battery, and that can stop the shorting. Second is also typically we use water-based liquid, so that's absolutely safe. What's most important thing for EV is actually you can just drain out the electrolyte. So if you have time, you can still charging. But if you don't have time, you can go to the gasoline station. But instead of making gasoline, you can actually using this liquid fuel into your car, and then the used liquid can be removed from the car and to be charged at the station, and using more solar, using more wind. And then you can charge it slowly because nobody cares how long it does it take because the driver already gone, right? The next driver will come, they can continue to use. So this can really decouple the charging and the discharge part and make a much more flexible way of using renewable energy and make a better user experience. So that's sort of our dream, but so far it's still on the way. Why nobody is using flow battery for car? Again, energy, right? All the reason is energy because the energy density is too low right now. In order to be as good as Tesla, we need 200 watt-hour per liter. And the least we need to get 100 watt-hour per liter to be as good as Nissan Leaf, right? So far, flow battery is only at 25 watt-hour per liter. So we have a long way to go. Recently, our group has been working on a high density flow battery called zinc iodide bromide, and that can get us 100 watt-hour per liter. Again, it's not as good as the best Tesla, but it's still reaching to Nissan Leaf, right? So you can see if I'm using same amount of energy, the ZIBB will be similar size with the lithium iron phosphate, the lower class of the lithium ion battery, right? But it's already much better than some of the vanadium flow battery, the state of the art in the flow battery industry. And so this also showed that the new chemistry can really boost up the energy density that you need to solve that issue that people don't want to use it because it's low energy density. And then with this liquid, you can quickly swap this in the station and then refill within 5 minutes. So that's kind of our vision. We have graduate students and postdocs working on this. But again, there are a lot of challenges to solve. So to summarize, I think science and technology is at the heart of the current industrial revolution, that we try to make this positive influence of economic growth and environmental protection. So hopefully all this little small technology advance will help us to get there someday. Okay, so with that, I'll end my talk and we can move on to the discussion.